very important implementation. You can consider this as an example of implementing logic functions by using the NAND gate. So first thing that we have to see is the number of NOT, AND and OR gates. To implement B complement and A complement, we need two NOT gates, and to implement A and B complement, A complement and B, we need two AND gates, and finally we require one OR gate, and as I have already explained, in case of NOT gate we require one AND gate, in case of AND gate we require two NAND gates, and in case of OR gate we need three NAND gates. So let's try to calculate how many NAND gates we require to implement the XOR gate. For NOT, we require two NAND gates, one for each. For AND, we require two NAND gates, and we have two AND gates, so we'll have four NAND gates. And for OR, we need three NAND gates because we only have one OR gate. So in total we require 9 NAND gates to implement XOR gate. So let's do it quickly. First we will implement the two NOT gates. So we will make two NAND gates, and we will provide similar inputs to these two NAND gates so that they work as NOT gate. This is A, this is B, and now we will implement the two AND gates. Okay. The output of AND gate is A and B complement, so we will take A from here, and this will act as input for this NAND gate. So the output here is A and B complement, and for the second AND gate, A complement and B is the output, so we will take B from here, and the output here is A complement and B. So you can clearly see these two NAND gates, and these two NAND gates are working as AND gate, and this NAND gate here and this NAND gate here are working as NOT gate. So we have implemented the two NOT gates and two NAND gates. The only thing that we have to do is to implement one OR gate. So I will implement one OR gate, and for this we require three NAND gates. First we will use two NAND gates as inverter, and then we will use the third NAND gate to get the output of OR gate. So let's do this quickly. First we will have inverter, and this is Y, the final output, and it is equal to A and B complement or A complement and B. You can easily prove this. This gate is working as NOT gate. This gate is working as NOT gate, and the input is A complement and B. So we have output as A complement and B and its whole complement. In the same way, here we have A and B complement and its whole complement. Here Y is equal to A complement and B, its whole complement, and A and B complement and its whole complement, and finally we have complement of all. We will use De Morgan's law to simplify this. Y is equal to A complement and B, or A and B complement. This is A XOR B. So we have implemented the XOR gate by using the 9 NAND gates, and this is not the best way, to implement the XOR gate. We can implement XOR gate by using 4 NAND gates only, and here we are using 5 extra NAND gates. So let's see what is redundant in this circuit. We are using NOT gates like this, And if you use NOT gates in this manner, let's see what we have. If A is the input of this NOT gate, here we will have A complement, and finally we will have A again. So we are getting the same function by using the two NOT gates in this manner. So there is no need to use this 4 NAND gates. We can eliminate this 4 NAND gates from this circuit and will still have the output equals to A complement and B, or A and B complement. So we have reduced 4 gates from 9, and now we are using 5 NAND gates to implement XOR. But still we have to get rid of one NAND gate because it can be implemented by using 4 NAND gates. So let's see what we can do. First I will make this circuit again, and now I won't include this 4 NAND gates. This is A, this is B, and I'm not going to use these 2 NAND gates. So the output of this NAND gate will go to this NAND gate here. In the same way, output of this NAND gate will also go to this NAND gate, A and B. So we are using 5 NAND gates. At this point we have A complement and B and its whole complement, and at this point we have A and B complement and its whole complement. We are getting this too by using 4 NAND gates, but we have to obtain these results by using 3 NAND gates. Here we are using 4 NAND gates to obtain this too, but we have to use 3 NAND gates. So let's see how we can have the same results by using the 3 NAND gates. First I will draw it and then I will explain. This implementation is very important. Y is equal to A XOR B. So instead of using the 4 NAND gates, now we are using 3 NAND gates in this manner, A, B. Now we will check whether we are getting these 2 results or not. Output of this NAND gate is A and B and its whole complement. Output of this NAND gate is A and B, its whole complement, and finally the complement of all. In the same way, here we'll have this, and now we have to simplify this. So let's do this quickly. I will use the De Morgan's law. A complement or A and B. Here we'll have B complement or A and B. And if you remember the Boolean algebra, I told you if we have X complement or X and Y, it is equal to X complement or Y. In the same way, from here we'll get A complement or B, and from here we'll get B complement or A. A complement or B can be written as A and B complement and its whole complement, and B complement or A can be written as A complement and B and its whole complement, and you will find we have the same results, A complement and B and its whole complement from here, and A and B complement and its whole complement from here. So we can say that this is the most efficient implementation. This is very important because you have to use your brain to get this circuit. We started from this circuit, we had 9 NAND gates, then we had this circuit with 5 NAND gates, and finally we have this circuit with 4 NAND gates. So this is the most efficient implementation, and please draw it somewhere so that you can revise it before your exam. Now we will move to XNOR implementation by using the NAND gate, and you already know to obtain XNOR we complement the output of XOR gate, we complement the output. If A and B are the two inputs, then output Y is equal to A and B, or A complement and B complement. So implementation of XOR gate by using the NAND gate is very simple, and this will require 4 NAND gates. So first we will make XOR gate by using 4 NAND gates, and then to complement the output we will use one inverter, and this will require 1 NAND gate. So 4 plus 1 is equal to 5 NAND gates. 5 NAND gates are required to implement the XOR gate. So this is all for this lecture. Now we will move to homework problems. I have 2 homework problems. In first homework problem, you have to find out minimum number of 2 input NAND gates required. In first homework problem, we have to find minimum number of 2 input NAND gates required to implement X complement and Y and Z. So you have to implement this function X complement and Y and Z, and you have to tell me the minimum number of 2 input NAND gates required. You have to follow the procedure same as implementation of XOR gate. And in second homework problem, you have to find the minimum number of 2 input NAND gates required to implement X and Y, or W and Z. So these are the 2 functions, and you have to implement them by using 2 input NAND gates, and the number of NAND gates should be minimum. Like in case of XOR gate, we can implement it by using 9 gates, 5 gates, and also we can implement it by 4 gates. So the correct answer is 4 NAND gates because it is minimum. So this is all for this lecture. Once you have your answers, post them in comment section.